Welcome to another video. In this video, we're going to talk about some of the basic properties of trig functions: sine, cosine, tangent, cosecant, secant, and cotangent. Just as they relate to each other, start building some of these ideas called identities. And toward the end of this video, we're going to start talking about that. How identities let us discover a lot more about trigonometry than we would know just by given one trig function. So we can extrapolate from that or infer from that based on these identities that we're going to start unpacking right now. So we're going to take a look at a unit circle very quick. Talk about what sine and cosecant, how they relate to each other in terms of the x and y coordinates of the points on a unit circle. Same thing with cosine and secant, same thing with tangent and cotangent. So let's get started. When we talk about sine of some sort of an angle that's swept out counterclockwise positive on a unit circle, or any other circle for that matter, but unit circles is very convenient for us, is when we correlate these things with the sine of an angle and a point that's on a unit circle, we understand, hopefully, because I explained it lots, that sine of whatever angle this is going to be given by the y coordinate of whatever that point is. So in our case, we're going to have sine of theta equals y. Remember what trigonometry does. Trigonometry relates an angle to actually a ratio of y over 1, or the opposite over the hypotenuse, and the hypotenuse is 1 because we're in a unit circle, of a right triangle. And so we're always doing that. We can't just say sine equals, it doesn't make sense. But sine of some angle is going to equal the y coordinate of a point on the unit circle. Well, because cosecant is this idea of a reciprocal relationship to sine, we can define cosecant of theta as 1 over that y. Notice what this is doing. Because sine theta is y over 1, I know that 1's not there, but that 1 is that radius right there. Y over 1, if you reciprocate it, is 1 over y. Or, instead of looking at this, if you remember, opposite over hypotenuse, cosecant would be hypotenuse over opposite for whatever angle that is. This is going to play in pretty big when we start talking about domain, because while y, we're going to get all real numbers, we're letting the cat out of the bag here, cosecant we're not. Because what's going to happen is when y equals 0, that becomes a problem. Do you remember that? I hope you remember that. How domain, when we have fractions, it's an issue when our denominator equals 0. We get some undefined values, so we get some domain issues, things that we cannot plug in. And we're going to get that here. How about cosine? Well, cosine theta, when we take a look at this, cosine we've associated with the adjacent, or the x side of this. So when we take a look at our unit circle, cosine of whatever angle we're sweeping out is going to be the x coordinate. We can think of this as adjacent over hypotenuse. That would be the adjacent side, or x side over the hypotenuse of 1. That would give us just x. Because secant is defined as the reciprocal of that cosine, we can put 1 over x here. So instead of adjacent over hypotenuse, it's hypotenuse over adjacent. That's 1 over x. I know that I'm relating this back to the right triangle, and I'm doing that on purpose because we're going to get there. It's a really long time from now, but I don't want these two things to be separate. I want you to understand that whether we're talking about sine, cosine, tangent, these trig functions on a unit circle or a right triangle, we're talking about the same thing. We can relate them the same way. One of the main differences here is that we can also talk about arc length as it relates to a unit circle. But in general, I want you to understand that how sine is associated with the y output, or the y coordinate, but it's also associated with opposite over hypotenuse. That same thing for cosine, tangent, and all the reciprocal functions. We can relate them both ways. Now for tangent. Tangent is this idea on a right triangle of the opposite side over the adjacent side of a right triangle. But for us, that would be a y over x. We can also get sine over cosine. And likewise for cotangent, we're going to reciprocate that and get x over y. We can think about that in a right triangle as adjacent over opposite. Those are really the major relationships that we have when we're thinking about trigonometry on a unit circle. Now we're going to get to inverse functions eventually as well, where we're going to be using a unit circle in a slightly different way to go backwards. But as it stands right now, I really need you to get that. I need you to understand that sine, cosine, tangent, have reciprocals, cosecant, secant, and cotangent respectively. I need you to understand that sine of theta relates an angle to the y-coordinate. Cosine is an angle to the x-coordinate. Tangent is an angle to the ratio of those two things. And that's really important. So now we're going to transition just a bit. And we're going to talk about domain and range of these trig functions. And we're going to do it just by looking at what the outputs could possibly be. So let's start with sine. Remember, when we're looking at domain, we're trying to think, what can I plug in that gives us an actual output? Not just plug in anything you want. What can I plug in or evaluate into my function that's actually giving me something? And so really what we're looking at is what angles give us some realistic outputs here. That's how we're going to start to find our domain. We're going to start with sine and work our way through this. We'll do all of the domains and ranges of each of these functions as we go because they interplay off each other a lot, especially when we get down to tangent and cotangent. So just remember with domain that one issue we have is that if you ever try to divide by 0 or something gives you an output that is divided by 0, that input's not valid. I'm going to repeat that a slightly different way. What we're looking for is to exclude any angle. That's our inputs. Remember, we're talking about domain here. Exclude any angle that will give us an undefined relationship, something over 0. So let's take a look at that for sine. If we think about sine, and if sine is the y-coordinate, that's why I kind of pounded that into your head just right now. If sine of theta is giving you the y-coordinate of whatever these points are in the unit circle, well, let's look at y. The y-coordinate starts at 0. So for this angle, you start at 0. And it's going to get larger, 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 larger until it peaks at 1. 1 is the largest value that we can get for y. And then starts dropping again, dropping, 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 dropping. Remember, I'm focused just on the y-coordinate. It's just sine. I'm going to show you a slightly different way in just a second. And then it starts dropping, dropping, dropping. Y starts becoming negative here until you get down to -1. That's the lowest it ever gets. And then it starts climbing again. Still negative, but it's getting closer and closer to 0. And then it starts to repeat. So for our y values, are there any y values that are undefined? Well, what I'm asking is there anything that I have an angle where my y value is like, I don't know, or I get something over 0. Well, no, that's not true. I'm going to show you a slightly different way. I'm going to use my left hand on the y-axis and my right hand to go around the circle, and check this out. As we climb, the y value just gets higher. I'm going to switch. It gets lower. It bottoms out at -1. And then it comes back to 0. So all my finger did, all my y-axis finger did, is it moved from here to here, then from here to here, back from here to here, and then back from here to here. When we get to graphing, I'm trying to make the connection right now. When we get to graphing, sine is going to do exactly that. It's going to climb, fall, climb. From 0 to 1, back to 0 to -1, back to 0. That's what the sine function is going to look like, just this nice repeating curve. What do you mean repeating? Well, as soon as you make one full rotation, this 2 pi, you're going to get back to where you started, and you're going to start getting the same exact y values over and over again. That's called a period. We're going to get there in just a little bit. So if we're looking at this, think about your angles right now. Are there any angles that give you this undefined output? Are there any angles that give you a y that's not on here? Well, no. The only y's that we're getting out are from 0 to 1, and then from 0 to -1, back and forth between that. So all of our angles, all of our thetas, are actually defined. We can plug in any angle, and it's going to give us this actual y value. It just goes from 1 to -1, or -1 to 1. That's it. So what we're going to say is that for sine, we're going to get all real numbers. There's not an angle that you can't plug in that's not going to give you something in terms of sine. So that y is always defined for us. It's always between -1 and 1. And that's exactly what we're going to get for our range right now. So you can plug in any angle that you want. Notice that, anything you want, anywhere on the circle, as many times around as you want to go. But ultimately, your y-axis finger is just going to go from here to here, somewhere between there. Well, how many numbers are between -1 and 1? An infinite number of them, but you can't get outside of that. Well, that's the range. The interval of outputs that you can get is called your range. Now, you can plug in anything, sure, and get out something between -1 and 1. So our domain is Theta can be all real numbers, anything that you want to, as many times around as you want to go, positive or negative, but you can only get out -1 to 1. Now, there's no hidden missing numbers in there. It's continuous here from -1 to 1 as far as our range is concerned. But we don't have anything undefined. We don't have anything outside that. So our range is you can get out -1 all the way to 1. We're going to use a bracket to represent that. So we can show it two different ways. We can show interval notation -1 to 1, or we can show this with inequality notation here. -1 bracket and 1 bracket the sine theta. That's the large you can get. Remember, this is actually y. And so we can see that y never gets less than -1, never gets bigger than 1. I know I spent a lot of time on sine, but the rest of these are going to flow from that. So that, or at least the idea. Let's look at cosine. Cosine is just x. Remember, cosine of whatever angle you have is mapped to the x coordinate. Let's look at x the same way we did y. If I start here with an angle of 0 radians or degrees, and I start going positively around my circle, our x starts at 1. This is the point, 1, 0. As we start going, my x gets smaller until it gets to 0, then it starts getting negative until it gets to -1, then it gets grows again until it gets back to 0, and then positive until I get to where I started. So for the same exact reason that sine has a domain of all real numbers, cosine also does. You can plug in any angle and it's going to give you some sort of an x value. Nothing that's undefined, nothing that's outside of the range of -1 to 1. And so these look very similar. So cosine of theta, the domain for theta is all real numbers, whether you're talking about sine or whether you're talking about cosine. Remember that both of these things relate an angle to some sort of an output, x for cosine and y for sine. Our range is also the same. You can get out for cosine -1 to 1, anywhere along that interval of the x-axis. Remember, we're just looking at x right now. I want to point out a few things, just some common misconceptions that students who are just seeing trigonometry the first time or really have never understood it make. The first one is that while sine and cosine have the same range and they have the same domain, they're talking about different things. Remember, trigonometry really relates three pieces of information. It relates an angle and a ratio of two sides, or an angle and some way of relating these coordinates of a point. And so what we're talking about here is really a different type of domain. I know that you're used to a domain being an x-axis idea. That's true for all of our functions that are defined in terms of x and our outputs in terms of y. But really we have one type of input, which is a domain of an angle. And so when we're talking about domain, we're talking about what angle can this actually get? Well, sine, you can give me any angle. Why? Because our outputs are one of two different types of outputs, a y or an x, or a comparison of them. And so our inputs are angle ideas, not an x idea. And that can be confusing for students. That's the second thing that people get confused on, is they say, well, I thought my domain was just -1 to 1. And it's not. That's actually your range. So the first thing is that sine and cosine are different. They're not the same thing. The second thing is that when we start talking about domain and range, it's a little different from normal. Our domain is what angle can you plug in? Any angle will give you out some sort of a real y value for sine and some sort of a real x value for cosine. I hope you're seeing that. I hope you're seeing that the domain is different than normal. It's not just an interval of the x, it's an interval of an angle. So an interval of where you can go on a circle, what radians can you get or degrees can you plug in and get something out for sine. For sine and cosine, it's any angle will give you a y or an x respectively. What can you get out for those y's and x? Well, now the x-axis gives you this interval for cosine, this range for cosine, and the y-axis gives you an interval or this range for sine. And that's an idea. It's completely different, right? And so our domain is, yeah, you can plug in any angle, but for sine, you can't get out anything besides -1 to 1 or some value between there. For cosine, it's an x-axis idea. You can't get out anything from -1 to 1 or some number inside of that. Along the x and along the y for cosine and sine, respectively. And I hope I'm making that makes sense to you. The last thing I want to talk about is graphically. Notice how sine, when I start at 0, sine starts at 0, gets larger, smaller to 0, negative, and then back to 0. Cosine does that, but shifted. And we're going to get an identity later that says that. But cosine starts at 1. So cosine is going to start at 1, drop to 0, go negative, and get back to 1. So it's a different looking graph. They're very, very similar in how they're shaped. And in fact, there's an identity to transfer one to the other, to translate a little bit, to shift it. But for now, I need you to understand they are different, even though they look very similar, because one is a y idea and one's an x idea. Okay, I've talked a lot about that. Let's talk about tangent now. Tangent's different. You see, tangent takes a relationship. It says, what angle can you plug in such that I get a real defined output out? Well, we know something about domain. We know that we can't plug in numbers that cause us to get some sort of fraction with 0 on the denominator out. And so we're really going to start taking a look at that first. I'm actually going to define the range first and then the domain. Why? Well, because the range is x's and y's. The angle is what angle causes, the domain is what angle causes that output. So we're going to take a look at some outputs for tangent that we really shouldn't allow. Remember that tangent is y over x. And so we're going to look for this as, all right, if it's y over x, then our x, where our x is 0, we have a problem. So let's start taking a look at our unit circle. Here our x is 1, that's no problem. Remember, we're looking at tangent as this y over x. So let's see, 0 over 1, that's fine. And we're going to get positive number over positive number, that's not a problem, until we get to right here. At that point, we have the first instance where tangent would have a major issue. Tangent is 1 over 0 here. Remember, if x is 0, this is a problem. Our x starts from 1, and as we're going around, it goes to 0 here, negative, and then back to 0. So at the first and third quadrant angles, at pi over 2 and at 3 pi over 2, we have some major issues. And so we've sort of taken a look at the range when we're thinking about this, thinking what outputs are wrong, and then eliminate those inputs, that angle from the domain of tangent in this case. So we said, hey, look, x is 0 here, that means at pi over 2, we're going to get something that's undefined. Well, what that means is that input, that pi over 2, is not allowed for tangent. Same thing happens as we go all the way to here, 3 pi over 2. That means at 3 pi over 2, that input is not allowed because it would give us -1 over 0. That's something over 0 that's undefined. So we've taken a look at range, and now we're going to define our domain because of that. And so that's pi over 2, 90 degrees, 3 pi over 2, 270 degrees, 5 pi over 2. And you can see that we can go around the circle positively or even negatively. So like negative pi over 2 and have some domain issues with tangent. We're going to have a slightly easier way to write that in a little bit. But this is just your idea. So every pi over 2 that you get, pi over 2 or pi over 2 plus or minus pi, that we have an issue. 90 degrees, 270, or another 180 degrees past that, or subtracted from that. We're going to have some major problems here. I hope you understand that. I hope you're understanding that there's certain angles of tangent. Because x can take the value of 0, right there, that we're going to have some issues with. Now, what's our range? Well, this is quite interesting. For tangent, because tangent takes two values, y and x, and puts them in ratio, y over x. X can get very, very small when y is close to 1. Well, what that means is you can get some very, very large numbers. And say that again. When y is close to 1, x is very close to 0. So what's a number very close to 1 divided by a number very, very close to 0? It's getting close to infinity. So as we approach this pi over 2, we're getting close to infinity. That's why we can't even plug in 1 over pi over 2, because we get 1 over 0. That's taking 1 divided by 0. How are you going to divide 1 by 0? It's undefined, but just to the left and right of that, we're close to positive or negative infinity. We're going to see that graphically in just a little while. So our range is, you can get out anything for tangent. Now that we've dealt with these, we can deal with the reciprocal functions quite nicely, as long as you understand this idea. The idea of why these can't happen is because of those inputs would give us an undefined output. That's a problem. So that means we can't allow that in our domain. If you understand that, hey, taking a ratio of two real numbers on an interval of 1 to -1 or -1 to 1 for both of these cases, you can get anything out of that if you divide them in those relationships that I've shown you. Like, hey, y is getting real close to 1 and it's getting real close to 0. 1 divided by something real close to 0 is getting to infinity. Well, if you understand that, then we're going to get some very similar things here. I want you to think about cosecant. So cosecant of theta says what you're going to do is you can take 1 over y. Well, wait a minute. This is going to have problems if we allow some angles that let y equal 0. So all we've got to do is look at our unit circle and realize that, hey, if sine gives us y and cosecant is 1 over that y, then where y equals 0, we have issues. Other places are going to be fine. But here at this angle, 0, we're going to have a problem because this is going to try to take 1 over 0 and then, oh, well, that's positive y all the way from here to here. That's going to try to take 1 over 0. This is negative y from here to here. That's fine. So we're going to have two values on the first revolution around the circle that are not allowed, at 0 and at pi. And so on and so on. And if we talk about degrees, that'd be 0 degrees and 180 degrees and 360 degrees and every 180 degrees past that. So we can go round and round and round. And every so often, at every one of those times where our y is equal to 0, we'll have something that, an angle that we can't plug in, that we can't evaluate, that is giving us an undefined output. And so what this means is that in terms of our range, we can get out something kind of strange. You see, this is kind of interesting, but if we're going to start dividing 1 by y, remember, that's what this is, right? This is 1 over y. Well, y's largest value is 1, and y's smallest value is -1. So if we divide 1 by 1, sure, we're going to get 1. Or 1 by -1, we're going to get -1. But 1 divided by something between there. Remember, this is between -1 and 1. Well, all those values are smaller than 1. 1 divided by something that's mostly smaller than 1 is going to give you values larger than 1. What? In fact, the closer you get to 0, the larger these numbers are. That doesn't change. That oscillates between -1 and 1. So 1 divided by -1 is -1. That's actually one of our bounds of this, of our range. And 1 divided by 1 is 1. But 1 divided by, let's say, 0.5, well, that's 2. Or -0.5, that's -2. Or let's say 1 divided by 0.1, well, that's 10. These numbers can get really big. 1 divided by 0.000001. Can it be there? Yeah, we can have that. Here's y, that's very, very small. 1 divided by very small numbers is very large. Or very small negative numbers is very large negatively, if you will. So what our range becomes is, we can get out a lot of negatives up to -1. And then 1 to infinity. So the only things we can't get out is this interval between negative 1 and 1, it should make some sense that I'm basically reciprocating everything, right? So we're going to get this outside idea of negative 1 to 1. Sure, we can get out negative 1 and 1 just by dividing, but remember that y is bound by that. Can only be smallest value negative 1, largest value 1, everything else is between there. And dividing 1 by a number smaller than 1, you're going to get values larger than 1 or outside that range of negative 1 to 1. Now, how about secant? The same exact thing happens here. You can probably see it. It's just that our domain's going to be different because we're looking for where our secant is 1 over 0, where x is 0. So where is x 0? X is 0 at pi over 2 and 3 pi over 2. Now, why in the world would this have the same domain as tangent does? Why? Well, this says if I take y divided by x, where x is not, where x is 0, that's giving us issues. And this is saying the same thing. Look at our denominator. Here's a denominator of x. Here's a denominator of x. Y is defined everywhere. 1 is a constant. So the only issues we could possibly have are where x can equal 0. They're the same exact angles where x can equal 0. Remember, our inputs are angles here, where our angles are pi over 2, 3 pi over 2, 5 pi over 2, and etc. You're going to get x values of 0. That makes these inputs give us an undefined output for both of those cases. Now, our range is going to be the same as for cosecant, but remember we're talking about a different output. This is 1 over y. And this is 1 over x. So he's talking about x values. Okay, last one, then we're going to talk about the periods of all of these trig functions. Period is how often they repeat, so we'll talk about that in a little bit. How about cotangent? Well, for the same exact reason that secant matches up with tangent, cotangent is going to match up with cosecant. Well, what does that mean? Cosecant says if your y equals 0, you got problems. Well, same thing with cotangent. If your y equals 0, you got problems here. So cotangent takes the relationship of the x divided by the y. So any angle that gives us an output where y is equal to 0 is going to give us a problem, something that input is undefined. And so what we're going to say is that our theta cannot be the same exact values that our cosecant is. Cotangent is creating this relationship of an angle to the x coordinate divided by the y. Cosecant is creating this relationship between an angle and 1 over y. So where this equals 0 is the same place where this equals 0, and both of those would be undefined. So we're just going to basically copy down those. So at 0, your y is 0, and at pi your y is 0, and at 2 pi your y is 0. And lots of other places as we keep going around and around that unit circle, both positively and negatively. For the same exact reasons that tangent of theta can give you an output of all real numbers anywhere, y divided by x, same thing happens here. X divided by y, well, x is all real numbers and y is all real numbers. The only things that we're excluding are where your y is 0. You can get everything out of that as well. I probably could have just given all this to you and said, hey, here's your domain. But I hope that you stuck with me and that you walked through it and understand why it is you can plug in any angle here. Hopefully you understand a little bit more that what trigonometry does is relates an angle. That is what you're plugging in here. That's what you're evaluating. And your outputs are something on the x-axis or something on the y-axis or ratio of those two things. Hopefully you understand that now. So our domain is talking about what angles can you plug in? Any of them, because your y is defined between -1 and 1 everywhere. For cosine, any of them, because your x is defined -1 to 1 everywhere on the x-axis. Tangent, you can't plug in things where your x is 0. Well, that's going to be these particular angles. You can get out of everything because of that ratio. Cosecant, you can't plug in things where y equals 0. Any angles where y is going to be 0. Why? Well, because it's based on your sine. And your cosecant, you can't plug in anything where x is, any angle where x is going to be 0. And that's why we exclude those. Cotangent, you can't plug in anything where y is equal to 0 again, because that's the reciprocal of tangent. So hopefully you understand a little bit more about where that's coming from. We'll talk about what our periods are in just a second. When we hear about what a period is in trigonometry, it's an interval on which, a repeatable interval, on which your outputs of that trig function repeat. And so the idea of being a repeatable interval on which your trig function's output repeats, what that means is that we can really repeat a lot of the outputs every so often, and that period's going to really help us on graphing, really understand what these trig functions are all about. So let's take a look at what this period means, this interval of repetition for your trig function. Basically, let's take a look at sine. So what we're looking for is, where is this repeatable repetition of your output happening? Well, here's our outputs. Our sine is in blue here, so here's 0, here's 1/2, √2/2, √3/2, and 1. And I want to show you something on how to really think of this if you want to memorize your unit circle really quickly. Here it is. Sine always counts up, and cosine counts down from where you start. So check this out. Here's √3/2, √2/2, √1/2, and √0/2. This is actually √4/2. So if you think about that, this is the square root of 4/2. That's 1. Square root of 3/2, square root of 2/2, square root of 1/2, square root of 0/2. So you can count down with cosine. Sine counts up. Square root of 0/2, square root of 1/2, square root of 2/2, square root of 3/2, square root of 4/2, and then counts back down. It's a nice way to remember that. But let's look at, that's just a side note, but let's look at the outputs of outputs as it relates to our angles, which are our sine outputs. So 0, 1/2, √2/2, we get our output starting to repeat right here. And you go, oh, then our period is a repetition from here to here. Well, I suppose, but it's not repeatable, because this angular distance from here to here is not the same as from here to here. Even though those outputs are the same, the angle is pi/4 and 3pi/4, 45 degrees and 135 degrees. That's not the same distance or angle movement, if you will, as it was from an output of 1/2 to 1/2. So we're not going to consider that to be a period. What we want is this: every single output is repeated on this particular interval of an angle. Well, what's going to happen is we don't get another 1/2 past this one until we get all the way back on 1 full revolution, or 2 pi. The period of sine is 2 pi. Well, for cosine, we have exactly the same thing. We get 3pi/2, and the next time we see 3pi/2 is all the way back right here. Well, that's great, but the other outputs of x, or cosine theta, they're not repeated in the same interval as that. So this √2/2, that's repeated a lot sooner than that √3/2 was. So what we're looking for is this interval, this angular interval on which all of our outputs are repeated that often for x. And that also is 2 pi. I'm going to explain that here right now. So we don't get back to square root of 2/2 and 1/2 until we make 1 full revolution. That's the same exact interval on which we're getting those outputs back. So sine and cosine both have the same, what we call period. This same interval on which we're going to start repeating all of our outputs for both y and x. Now, tangent's weird. We might think, well, tangent's going to be 2 pi also, but it's not. It's not, because what we're looking for are this interval on which all of our outputs are starting to be repeated. Well, for tangent, that's sooner. And it has to do with the signs. This positive divided by negative, negative divided by negative, giving us a positive. So check it out. On pi over 4, we get square root of 2 over 2, divided by square root of 2 over 2. That's what tangent would be. Tangent is y divided by x. We can see that right here, sine over cosine, or y divided by x. So that's going to give us 1. But right here, we also get 1. Negative square root of 2 over 2 divided by negative square root of 2 over 2. That gives us positive 1. So for tangent, we can see it here, pi over 3 and 4 pi over 3, we have the same relationship. These are both positive. These are both negative, but when we divide them, they give us the same output. And so because we relate tangent as y over x, and because positive divided by positive and negative divided by negative are both positive, positive divided by negative and negative divided by positive are both negative, we're going to get a period, or this interval on which all of our outputs for our trig function tangent repeat, is pi, not 2 pi. Now, what's very nice is that cosecant and secant, because they relate to sine and cosine respectively, we have the same periods. And the same thing for cotangent as it relates to tangent. So what this does is this gives us what is called an identity. What an identity is this truth about trigonometry that works all the time and allows you to extrapolate information from it. So here's our very first identities. Well, kind of third ones. I didn't call them identities, but that's one of them. Tangent equals sine over cosine as far as our angles are concerned. So what these do is this says, okay, here's what we can do. We know that because our output sine repeats for every one of our outputs, not just some of them some of the times, but every one of them all the time on a period of 2 pi, a repetition of an angle 2 pi, that's one full revolution or another full revolution. Because that happens, we have this identity. We have this identity that, hey, if you have sine of some sort of an angle, then if you add 2 pi or subtract 2 pi or multiples of that, what's that k? That k is a whole number like 1, 2, 3, 4, 5. If you add multiples of 2 pi, so add 2 pi or 4 pi or 6 pi or 8 pi or subtract 2 pi, 4 pi, 6 pi, 8 pi, any product of that 2 pi, well, then you're going to get the same exact output. Really get this. It's going to make the rest of this make sense. Really get this. That sine of this theta, this angle, is a y value. Now go a full rotation. You're at the same y value. Go another full rotation. You're at the same y value. Do that a lot of times or negative a lot of times. You're just getting the same y value. All this says is sine your y value, basically. Sine of your angle plus or minus full rotations is the same y value as whatever that angle is. And so ultimately, you can add or subtract multiples of 2 pi and get the same output as it relates to sine. The same thing happens for cosine. Because cosine is your x value of whatever angle you have, that point on the unit circle. So it says, hey, cosine of whatever angle, you're going to get an x value. If you go a full rotation, you get the same x value. Either way you go, positive or negative, you're going to get the same thing. That's what this is. Any multiple of full revolutions is going to give you the same exact x value. You can see it all the time. So if you went to, let's say, pi over 6, your x value, your cosine of pi over 6 is 3 pi over 2. Go a full rotation. You're back there. Go again. You're back there. Go backwards a couple times. You have the same x value, same output. For tangent, it's quicker than that. So for tangent, because of the way that our positive and negative interact, positive divided by positive is the same as a negative divided by negative. Because of that, our period was sooner, and we have a slightly different identity. It says that if you start adding pi or subtracting pi from your angle, that tangent plus or minus some sort of a multiple of pi, 1 pi, 2 pi, 3 pi, 4 pi, whatever, you're going to get the same exact output as tangent of whatever this angle is plus or minus those multiples of pi. Remember what that k is just multiplying pi by some whole number. So 1 pi, 2 pi, 3 pi, 4 pi, and so forth. You can add or subtract that. We're going to get the same for these. It's going to look very similar. I'm not going to talk you through it. I'm just going to tell you that these are the same identities that we have here. We can add and subtract full revolutions for sine, cosine, cosecant, and secant, and half revolutions, pi, for tangent and cotangent, and get the same exact value out, the same exact output out, which gives us identities that we can use. So one thing this allows us to do is instead of like counting full revolutions and things like that, we can really easily translate things that are outside of our normal interval from 0 to 2 pi into something on there. So because we know all our periods, we know that sine, cosine, secant, and cosecant repeat. All of our outputs repeat every 2 pi, tangent and cotangent every pi, every half revolution, and every full revolution counted respectively there, that we can just start adding and subtracting those things. And so we're going to identify what trig function we have, what the period is, and then add or subtract, mostly subtract here, 2 pi for all of sine, cosine, cosecant, and secant, and pi, tangent, and cotangent, or multiples thereof, to get ourselves within that normal interval, that normal domain for us. And so let's try sine. So we know that sine has this period of 2 pi. That means I can add or subtract multiples of 2 pi. That's what that case says. It says any number of 2 pi's that you want, 2 pi, 4 pi, 6 pi, whatever, until you get down into that interval of 0 to 2 pi. So let's take a look at it. 19 pi over 2 that's a lot, and I have to count a lot of revolutions if I wanted to figure that out. But if I start taking 19 over 2 and just or 19 pi over 2 and start subtracting 2 pi, you can really do it this way if you understand that we're in terms of pi here. Just take 19 over 2, that's 19 pi over 2, and subtract 2, or 2 pi, and just keep on doing it. So subtracting 2, that's 15 halves. Well, what if we subtract it again? That's 11 halves. What if we subtract it again? Well, that's 7 halves. What if we subtract 2 again? That's 3 halves. So what that means is sine of 19 pi over 2 is the same thing as sine of 3 pi over 2. So we've just got to figure out what sine of 3 pi over 2 is. So we're going to go 3 pi over 2. That's within this 0 to 2 pi interval. That is going to be -1. And we're done. One thing I'll do, I'll let you in a little hint here. One thing I do is I look at my denominator. It's like 2 or 6 or 4 or 4. And I look at what my period is. So for sine, it's 2, and cosine, it's 2 pi, and tangent is 1 pi. And I'll multiply my denominator by whatever that is, 2, 2, or 1. And then I'll start subtracting that number until I get down to something that's in my interval. So for instance, 19 over 2. Okay, so 19 over 2. I'm going to take that 2, my denominator, multiply it by 2, because my period is 2 pi. That's 4. And I just start subtracting 4s. So 19 minus 4, well, that's 15. That's still not within my 0 to 2 pi if I'm starting to divide by 2. I would just start subtracting that until I get down to my 3. And then 3 divided by 2 is less than 2, so less than that full revolution. If that helps you, great. If not, then just start subtracting 2 pi. So that's 2 minus those fractions until you get down to something that's within your unit circle. We do the same thing with 9 pi over 2. So 9 pi over 2, We're still dealing with cosecant that has a period of 2 pi, so I'm going to start subtracting 2 pi. So I know that 9 halves minus 2, well, that's 4 halves. So 9 halves minus 4 halves is 5 halves. Minus 4 halves again is 1 half. This is the same thing as cosecant of pi over 2. So what's that mean? What's 9 pi over 2 mean? That means we're going pi over 2 9 times. Well, every 4 pi over 2's is going to give you 2 pi. Think about that. 4 pi over 2 is 2 pi. So if we just start subtracting 4 pi over 2 to match our denominator, we're going to subtract 4 from that 9. That's 5 pi over 2. Well, that's still outside of this interval here. So subtract again, that's 1 pi over 2. And that's exactly how we're getting this. You can show your work if you want to and start subtracting 2 like we did, or 2 pi like we showed, but that's ultimately what we're going to get. So cosecant of pi over 2, here's pi over 2. Cosecant is 1 over y. So we're going to get 1 over 1, which is 1. How about tangent? So tangent of 19 pi over 6. Tangent's period is every pi. And so I'm going to start subtracting, honestly, just my denominator until I get something within my interval. So tangent of 19 pi over 6, I'm going to start subtracting 1 pi. Intervals of 1 pi. Multiples of 1 pi, actually I should say. So 19 pi over 6, let's see, 19 pi over 6 minus 6 pi over 6. That's just pi, but I'm matching my denominator. So notice I'm subtracting 1 there. That would be 13 pi over 6. Now 13 pi over 6 is still more than 1 full revolution, so I'm going to subtract that again. That's 7 pi over 6. Now that's something that's on our unit circle, but I'm going to do one more step. So 7 pi over 6 is right here. Tangent would be negative 1/2, that's y, divided by x. That's negative square root of 3 over 3. So negative 1/2 divided by negative square root of 3 over 3. I'm going to do it in my head right here. You should work it out. Negative divided by negative is a positive. 1/2 divided by square root of 3 over 3. Those 2's are going to cancel. You're going to get 1 over the square root of 3, or square root of 3 over 3. Now I said I was going to do it slightly different. Well, what if we did one more? Remember that tangent, it has a period every pi. So we could make it so that we find some angle between here and here every time. So if we subtract 1 more pi, just 1 more time, it puts us back right there. So if I do that, so that's 1 pi over 6. Notice something, make it make sense that this period is actually pi here, because tangent of 1 pi over 6, that's 1 pi over 6, should be exactly the same. Here's pi over 6. 1/2 divided by 3, the square root of 3 over 2 is the same thing as negative 1/2 divided by negative square root of 3 over 2. You're still going to get 1/2 over square root of 3 divided by square root of 3 over 2. You're going to get those 2's cancel. 1 over square root of 3 is square root of 3 over 3. It's exactly the same thing. That shows you that the period of period of tangent is this pi, repeats every pi, because of those signs that we talked about earlier. You should try the next couple on your own. I'm going to go really quickly through them. I'm going to show you sort of my shortcut on how to do this. So what I always do, I take a look at my denominator, I look at my period, and I multiply by that number in front of my pi. 2, 2, 1. 2, 2, 1. So I'm going to take my sine. Sine has a period of 2 pi. I'm looking at my denominator of 4. That means that I'm going to be subtracting 2 pi from this. That would be 2 pi over 1, same thing as 8 pi over 4. So notice I'm taking this, multiplying by 2. That's going to give me my multiples of my fractions in the same denominator. So I'm going to take my 9 pi over 4 and subtract 8 pi over 4 from it. Why 8 pi over 4? Because that's still 2 pi. So that's why what I was talking about, take your denominator, multiply it by 2. That's the fraction that you want to start subtracting. So 9 pi over 4 minus 8 pi over 4 is pi over 4. That looks good. That's some value that's on our unit circle as far as our angle is concerned. That's going to be square root of 2 over 2. We know that y is our sine of whatever our angle is. Last one, cotangent. Cotangent has a period of pi. So I'm going to be taking 17 pi over 4 and subtracting, let's see, that's 1. 1 times my denominator, 4, that's 4 pi over 4. So I take my denominator, multiply it by the number that's in front of my period, and that's the fraction you start subtracting. So 17 pi over 4 minus 4 pi over 4. Remember that right there is still 1 pi. That's how we're getting it. Well, that's going to give us 13 pi over 4. Remember that we can always get tangent and cotangent down between 0 and pi. Well, what that means is that you should have some number on your numerator less than 4. For sine and cosine, cosecant and secant, you should have some number on your numerator less than whatever 2 times your denominator is. Always that. So if I keep subtracting, that's 9 pi over 4. That doesn't look like one of these angles here. Five pi over 4. Let's see. Here's 5 pi over 4. I could do that, but we could go further as well. Remember, if the period of tangent and cotangent is 0 to pi, then you can always subtract or add these angles until you get somewhere on this particular interval, right here. For sine, cosine, secant, and cosecant, it's the full rotation. And so what we're looking for is for tangent and cotangent to have this number less than that number. For sine, cosine, secant, and cosecant to have this number less than twice that number. That's 2 pi, somewhere in there. So that's going to give us this pi over 4. So cotangent of pi over 4, here's pi over 4, takes my x divided by my y. Now it's because they're both the same, you're still going to get 1. I hope that makes sense to you. I hope you're seeing the interplay on how we can use these identities and say, hey, let's just start adding or subtracting 2 pi or pi, or whatever our interval is, and multiples of that. You could be a little more fancy and not have to do it several times if you thought a little bit harder about it. I gave you the most basic thing I could think of there as far as actually doing it. What we're looking for is to get something that's on our unit circle with the same output. It's way easier than counting our revolutions to get back to that. So I hope that I've made it make sense. I'm going to come back with a couple more, but at this point, you really should understand that for these values of our trig functions that are more than 1 revolution, even for tangent, more than a half revolution, we can always get something for tangent and cotangent here, for sine, cosine, secant, cosecant on our unit circle by adding or subtracting the appropriate number of periods. Okay, a lot of students think these are easier. They probably are because we're not dealing with fractions, but the same thing holds. Remember that like cosine and secant have the same period. Well, they're basically the same thing, really. Sine and cosecant have the same period. And what that means for that period of 2 pi is we can also add or subtract 360 degrees. So whether you're dealing with tangent or cotangent, add or subtract 180. Secant, cosecant, add or subtract 360. And get down to the appropriate kind of usage of our unit circle, really. For sine and cosine, you should be somewhere on this full unit circle. For tangent and cotangent, somewhere on the half of that unit circle. So take a look at cosine 420. Well, that's way more than 1 full rotation. So let's subtract 360 degrees and see where we land. If we subtract 360 degrees, that's exactly the same we can do, then we're going to get cosine of 60 degrees. Now, cosine of 60 degrees is really easy to find. That's going to be 1/2. The same thing works with secant, actually. Secant has a period of 2 pi. So if we take 540 degrees, which is more than 360, more than on our unit circle right now, let's subtract 360. So secant of 180 degrees, just subtracting 360, it's going to give the same output. Now secant is this 1 over x. It's 1 over cosine, so 1 over x gives us -1. So we can do this with radian type measurements, we can do it with degrees. Degrees are typically a little easier because we can add and subtract 360 or 180 a lot nicer than we can these fractions of radians. But that's just about it. I hope I've made it make sense. I hope that you understand the interplay between our period and what we can do with it. I probably went a little overboard and did a lot of examples just so you could see the, hey, you know what? You're adding for 2 pi, 2 times that denominator, pi, every single time. And for tangent and cotangent, 1 times your denominator, pi, every single time. I've made that clear, but hopefully you see that. We're trying to end with something that's on our unit circle to make it easy. Well, I thought I'd give you a little extra here, a quicker way to look at how to simplify some of these angles that go more than 1 revolution around a unit circle, or even that don't in tangent and cotangent case. So I'm going to show you kind of a special trick. I already give you a basic way, and you certainly can do that by subtracting the period over and over and over for the respective trigonometric function. But I'm going to show you a quick way to do it. I hesitate because students use it like a trick without fully understanding it, but I think it's going to benefit you, so I'm going to give it to you anyway. So here's the deal. How we can simplify the angle of a trig function that goes more than 1 period around a unit circle is by dividing it in a special way and looking at the remainder upon division. It has to do a little bit with number theory, modality of number. So I want to look at 11 pi over 2. Now, obviously that goes around the circle a lot more times than just 1. So here's what I can do. What I do is I take my denominator, I multiply it by the period for sine in this case, which is 2 pi, and then I look for the remainder of my numerator divided by that thing. So here's what I'm going to do. I'm going to take a look at 2 times 2 pi. Now that's 4 pi. I'm going to take 11 pi and divide it by 4 pi. Now the pi's are going to cancel, so I'm really looking at 11 over 4. Not 11 over 2, 11 over 4. Or 11 divided by 4. So 11 divided by 4, 4 goes into 11 2 times. And if I subtract them, I'm going to get 3. This is irrelevant. This is how many times you complete the period on the unit circle. That's irrelevant. What matters is, imagine this. Imagine going around the unit circle 1, 2 times. Where you end after that is the important part. That's what that number tells you. So the remainder tells you how many or how far you go past the full revolutions here. This does not matter. This does matter, and this will tell you your new numerator of that angle. So 11 pi over 2 is going to be the same thing for sine as 3 pi over 2. Not over 4, 2, because the period is 2 pi. So that 4 gets divided again by that 2. So sine of 11 pi over 2 is the same thing as sine of 3 pi over 2. Take your denominator, multiply your period, divide your numerator by that number. Your pi's are going to cancel, and you're looking for the remainder. That becomes this new numerator, and it will be somewhere on your unit circle. Let's look at tangent. So tangent of 6 pi. Now, let's look at the denominator of that angle. That's 1. The period for tangent and cotangent is just pi. So I'm going to take 1 times pi. Well, that's just pi. 6 pi divided by pi is just 6. So I'm going to take 6 divided by 1 times pi is 1. So I'm taking 6 divided by 6. If I take 6 and divide it by 1, it goes in 6 times, and there's a remainder of 0. Now, what's this mean? 6 pi says what this means is you'll complete the period 6 full times. 1, 2, 3, 4, 5, 6 for pi. Or sorry, for tangent. So that period is pi, and you complete it 6 times. The remainder says where you go after that. So you end at 0. So wait a minute. That right here is your new numerator. 0 times pi is 0. Tangent of 6 pi is going to be exactly the same as tangent of 0. Why? Because if you go 6 pi's, 1 pi is half a circle. 2, 3, 4, 5, 6. You end right back where you started at 0. This just does it for you. So take denominator times period for your respective trig function, divide it, look for your remainder. That remainder is your new numerator, in this case 0. How about cosine? Cosine 8 pi over 3. Cosine has a period of 2 pi. We need to know that. So all 4 of these have 2 pi. All of your sine, cosine, secant, cosecant have a period of 2 pi. Tangent, cotangent's 1 pi. Let's take our numerator, that's 3, multiply it by your period, that's 2 pi. That's going to be 6 pi. And what I'm going to do is I'm going to take my 8 pi over 3 divided by 6 pi. My pi's are going to cancel, and I get 8 and I get 8 pi over 6. So 8 divided by 6, 6 goes into 8 one time. There's a remainder of 2. I don't care about this. This says you've completed one full period for cosine, that's 2 pi. Where our past that is 2 pi over 3 past that. This is your new numerator. So cosine of 8 pi over 3 is the same thing as cosine 2 pi over 3. This says how many periods you complete. This is how far past that completion you are. It will be somewhere in the unit circle. This is your new numerator for pi. So in this case, cosine 2 pi over 3, and you can figure that's is negative 1/2, because that would be the x-coordinate of that. Now, do you use your unit circle for that? I'm not really going that far. I'm just showing you how to get something that's on your unit circle. You figure out the rest. How about sine of 19 pi over 4? Sine has a period of 2 pi, so I'm going to take my denominator, multiply it by my period, that's 8 pi. 19 pi divided by 8 pi. Pi's are going to cancel. I'm going to look at 19 divided by 8. 8 goes into 19 2 times, with a remainder of 3. The remainder is what's important. This says you complete two full circuits around that period. So 2 rotations. And then what you're going to do is you're going to have a leftover of 3. That's your new numerator. That's sine of 3 pi over 4, not 8, because it's based on the fact that there are a period of 2 pi, not just 1 pi. So it's always your same denominator that you keep. This is just giving you your new numerator. That's on the unit circle. Let's see. That would be quadrant 1, 2, 3, quadrant 2, and then you're going to get square root of 2 over 2. Let's do tangent 19 pi over 6. So tangent 19 pi over 6, we're going to take a look at tangent. Understand the period for tangent is 1 pi. Take your denominator, multiply it by your period. So 6 times 1 pi is 6 pi. Your pi's are going to cancel. We're going to look at 19 divided by 6. Please recognize that you do tangent different from sine. Tangent has a period of 1 pi, that's half a circle, it repeats every half a circle. Sine is 2 pi, that it repeats on a predictable, repeatable fashion. So we're going to divide. 6 goes into 19 3 times, with a remainder of 1. That's your new numerator. So this is equivalent to tangent of 1 pi over 6. So you complete 3 periods, not rotations, not full rotations. That's not the thing here. It's you've completed 3 periods. Your remainder is 1 past that. So pi over 6, it would be the new angle that you can determine. Tangent of pi over 6 is going to give you that, let's see, 1/2 over square root 3 over 2, so square root 3 over 3. Now, cotangent has the same period as tangent does. So if our period is pi for cotangent, 4 times pi gives us 4 pi. Pi's cancel. We're going to look at 17 divided by 4. Can you do it in your head? Yeah, of course you can. 17 divided by 4. 4 goes into 17 4 times. It will complete 4 periods. The remainder is 1. So there's a 1 is your new numerator, pi over your original denominator. And cotangent of pi over 4 is a lot easier than thinking about that. Cotangent pi over 4 is going to be reciprocal of tangent pi over 4. So that's going to be square root 2 over 2 divided by square root 2 over 2. That's 1. Or reciprocal is also 1. So that would be 1. Last one, cosecant. Cosecant has the same period as sine. They're very related. And so we're going to say, hey, the period of cosecant is 2 pi. Denominator times your period. That's 4 pi, and divide. That's going to be 9 divided by 4. So take 9 divided by 4 and look for the remainder. If your remainder is 0, then you get 0. That's fine. But here our remainder is 1. 9 divided by 4 is 2 and 1/4. 2 full periods and 1/4 of the next one. Why you get pi over 2 and not pi over 4 is I just said it. 1/4 of the next period. Well, because the period's 2 pi, 1/4 of the next 2 pi is 1/2, so pi over 2. And that's exactly what we have here. So 9 divided by 4, 4 goes in that 2 times. With a remainder of 1, we get 1 pi over 2. So cosecant of pi over 2, well, we think sine of pi over 2, that would be 1, so reciprocal is 1. So we get 1 here as well. I hope that makes sense to practice that. If we understand the period of our trig functions, we can take denominator times period, divide, pi's are going to cancel, and then look for your remainder. That's your new numerator with the same denominator. Because we have periods of 2 pi for sine, cosine, secant, cosecant, and 1 pi for tangent, cotangent. Hope that makes sense. That's a little bit extra, but it'll make things much quicker for you. Hope that helps. Now, lastly, please remember that your sines are very important. And so you should be able to determine what quadrant your angle is in just by looking at the sine of whatever your trig function is. So for instance, let's say that you have this, you have the relationship that secant of your angle is negative, sine of your angle is positive. What quadrant would that angle be in? Well, let's think about this for a second. In quadrant 1, all of your trig functions are positive, every single one of them. In quadrant 2, only sine is positive, and that means cosecant is positive. Why? In quadrant 2, your x values are negative and your y values are positive. If your x values are negative, that means cosine and secant are both negative. Now we see that cosine is negative, but secant would also be negative. It's 1 over cosine. Tangent's also negative. Why? A positive divided by negative is negative, and cotangent's negative. Why? A negative divided by a positive is negative. So only sine and cosecant are positive here. And you can work your way around and kind of see that. Only tangent and cotangent are positive here. Only cosine and secant are positive here. Because of the interplay between the sines of our axes there, positive x and negative y, is going to create for you this, hey, negative y for these particular angles is going to say that sine and cosecant, tangent and cotangent are all negative in that quadrant. So going back to my question, what if you knew that secant was negative and sine was positive? Well, sine being positive says you're either here or you're here. Secant being negative says, well, you can't be over here, everything's positive here. That would put you in quadrant 2. It's useful to think about things like that. Let's think about what if cosine is negative and tangent is positive? If cosine is negative and tangent is positive, what quadrant would you lie in? Cosine is negative. Cosine being negative would be any of these two, but cosine negative. But tangent being positive would say, if cosine's negative, you're somewhere over here. Why? Well, cosine's positive here, cosine's positive here. So these are the only two quadrants where cosine's negative. But tangent being positive would say, I'd have to be in quadrant 3. That's the only place where, let's see, x's are negative, cosine's negative, but tangent is positive. Negative divided by negative would give you positive. You can think about things like that. On what quadrant, think about this on your own, would, let's see, secant be positive, but cosecant be negative? Secant positive and cosecant negative. Maybe pause the video and think about that. Secant positive would be either quadrant 1 or quadrant 4, because secant relates to cosine. Cosine's positive here, secant's positive here, cosine's positive here, secant's positive here. Everywhere else it's negative. Secant positive would be in these two quadrants. Cosecant negative, well, let's see, cosecant negative would be, cosecant's positive here because sine's positive here. Cosecant's positive here because sine's positive here. Cosecant is negative on these two quadrants. So if cosine is positive, that'd be, if secant's positive, that'd be in one of these two. But if cosecant's negative, that's in one of these two. This is only one that has both secant positive and cosecant negative. So I hope that makes sense. We really should be getting these signs down. Sine and cosecant have the same signs in the same quadrants. So do secant and cosine. So do tangent and cotangent. So take a look at your unit circle and just really get used to that. Hopefully that makes sense. We're going to come back with some more identities, talking about the reciprocal identities in the next video. Have a great day.